Okay, in this video I'm going to do problem 2. And in this problem it says, prove the statement if true, otherwise find a counterexample. And part A says the difference of any two odd integers is odd, and part B says if the sum of two integers is even, then one of them must be even. Well, in the last problem we made a little chart of adding even and odd numbers, and I'm going to say even and odd, even and odd. I've got 4 cases. I can either add an even to an even plus odd plus even, or odd plus odd. It's really sort of like 2 cases. Either they're both even, in which case their sum is even, or we have one of each, in which case the sum is odd, or they're both odd, in which case the sum is even. And so hopefully you can see that if the difference, now this was the sum, but it also, the same chart also works for the difference. The difference of any two odd integers is odd. That's false. And we can just write down a counterexample. For example, 5 minus 3. They're both odd, but their difference is not odd. Okay? So for part A, we can say false. And we can say consider 5 minus 3 equals 2. Now, this is a counterexample, but this isn't enough for this course. We need to at least label this and say both odd and their difference is not odd. Okay? That is the very minimum of showing your work on this problem. First of all, stating that it's false, and considering 5 minus 3 equals 2 as a counterexample. Okay? Where we're saying that they're both odd and their difference is not odd. Okay? Even better yet is to do something like the following. Say, you know what? Part A is really an if-then statement. It says, if I have two odd integers, then their difference is odd. So let me rewrite that as x and p being the statement that x and y are both odd, x comma y both odd, and q the statement that x minus y is odd. Okay? Then part A is the statement if P then Q, right? If they're both odd, then the difference is odd. And we need to disprove this. And we are going to disprove by showing an example where P which is the premise, is true, and Q, which is the conclusion, is false. And in fact, P being true, in other words, we want to show P and not Q is possible. And that works for this counterexample up here. P is the statement that x and y are both odd, 5 and 3 are both odd, and Q is the statement here that, and not Q is the statement that 5 minus 3 is even. And we have both of them true. Okay? And so that's a little bit deeper analysis of this problem, but you cannot just write as an answer 5 minus 3 equals 2 and then say that you've solved this problem. For part B, if the sum of two integers is even, then one of them must be even. Let's solve that one a little bit further down here. If the sum of two integers is even, then one of them must be even. Let's write that let's say false. And we're going to provide a counterexample. Same one, 5. If the sum of two integers is even. Okay, so we're going to use 5 and 3 again. 5 plus 3 is 8, and the sum is even, but one of them must, one of them must be even is false, because neither is even. Okay? And if we look back at this statement, if the sum is even, then one must be even. Let me do this analysis. Let's let P be the sum is even and Q be 1. At least one must be even. Then this statement in B is the statement if P then Q, and in order to disprove that, we show P and not Q, a situation where we have P and not Q. That is, we have a situation where we have the sum is even and not the case that one of them is even. Okay, so this is P and this is not Q. Okay, and so that's how our counterexample proves this disproves if P then Q. Okay. Hope that helps on this one.